So where are you from? You're from Spain.
Yes, I'm from Spain. I'm in Madrid now.
All right. So how is the weather?
Well, it's cold now.
Okay.
Even here in Spain, but it's cold now.
All right.
And you, how is it in Pakistan, right?
Yeah, in Pakistan, it's like sometimes it's sunny, sometimes it's too much cold. I think the weather is around 7 degrees Celsius.
Mhm.
Okay. Just I would like to start the event with your consent. So you can share your presentation also,
Yes. I
and
think
I
I'll
will
share.
just give a
I'll
brief
sh
introduction about you.
I
We'll
think I
start
can
with the
share my whole screen, I guess. Oh,
just a minute. And okay, I would like to briefly introduce about the presenter. His name is Dr. Michael Herraez, medicines. I hope I pronounced it correctly. Uh,
yeah, it's not bad. It's Miguel. Miguel. It's much
Miguel
easier.
Herraez. He's the founder of Tecnodigital School. He's an expert in the simulation and computational mechanics with ABAQUS and Python. He has done industrial engineering at Carlos University, Madrid, finishing his BSc in West Virginia University, and he served 1 year at the Airbus military in USA. He started a PhD on mechanics of composite materials at India Material Institute, and he worked as a visiting researcher at NASA Langley Research Center in Virginia. And after completing his PhD, he moved to Switzerland to uh, do his doctoral research. And he also served as lecturer in University in Carlos of Madrid. And I would like to say thank the presenter for his valuable time for the students and faculty members of National Textile University and National Center of Composite Materials, Pakistan. So I would like to uh, request the presenter to start the presentation.
Okay.
And
Well,
all right,
okay, I'll
all
go.
right,
I'll go ahead. Thank you very much for the presentation. And well, I will just get started because I have many things to to show you to tell you today. Um, so today we'll be talking about numerical simulation of composite materials, and I want to focus on this topic because it's a very hot topic and it's also a fairly complex topic. This type of materials, modeling this type of materials, is not an easy task. So this is the table of contents, the layout of the presentation that we will see. First, an introduction to composite materials in general. Then we will see a bit more in detail what is this multiscale modeling. After that, we will focus on the mesomechanical part, where most of the research and most of the industry is actually becoming more and more interested because of the level of detail that it allows. Then we will see a bit of experimental characterization. What are some of the main and not so main uh, experimental techniques to obtain material properties. And finally, we will see an example in ABAQUS. We will spend some time looking at one model and looking at some results and trying to understand what is going on this model. This will be in ABAQUS. So let's go ahead with the first part with the introduction. Well, first of all, what's a composite material? Just to set all of us on the same page. A composite material is made of several different materials, several different phases, which is commonly known as the primary phase or matrix, and the secondary phase or the reinforcement. This reinforcement could be anything, could be fibers, could be particles, could be platelets, could be long fibers, could be short fibers, etc., etc. And with this, we obtain a composite material. And the matrix agglomerates this reinforcement, keeping it together and protecting it from the surroundings. And there is also one more phase that appears when we combine these two materials, and it's the interface. We shouldn't forget this phase as well. Why composite materials have become so popular in some industries, especially especially in the aerospace industry? Well, because they combine two big advantages over traditional materials, over other materials like metals, and it's that they have high high mechanical properties. This is high stiffness, high strength, but and in addition to that, they also have a very low density, especially compared to metals. For instance, compared to steel or compared to even to aluminum, they are even lighter than aluminum. And that's why they have such high specific stiffness and specific strength. They have very high specific properties, which is the property, for instance, the stiffness, divided by the density. In this plot, in this graph that we have here on the right, what we have is the amount, the weight fraction of composite materials in civil aircrafts over the last decades, from the 80s, where we have some Boeing in yellow, Boeing planes, Boeing, where we have some small amounts of composites below 10%. And recently, from the last decade, we have even reached the 50% barrier of composite materials in the 77 or in the A350. So we see that this adoption of composite materials has been a huge trend in the aircraft industry. Well, we have this exception here, this Beechcraft Starship, which was developed in the 80s and has a 75%. It was sort of an experimental design, but it worked. They could use it, and it flew at the time. So yeah, the aircraft industry has taken and is impulsing all this development of composite materials. Here we have one example, one practical example. This is an A380, and we can see some parts, some sections that are made of these composite materials, these CFRP, J-nose, vertical tail plane, the outer flaps. Everywhere you see CFRP, this is carbon fiber reinforced polymer. We have glare, which is a fiber metal laminate. It's a special type of material. It combines aluminum and glass fibers in different plies in a single laminate. So we can see here many applications of these composite materials to a very recent development, which is the A380.
Share the presentation again. Can you share the presentation again?
Okay, presenting. It should be. Is it? Can you see it?
Not now.
No,
Just
no.
No, not now.
Okay, let me. I will try. I will try again. Okay, share again. Can you see?
Now.
Can you see it now?
Yes, we can see. Can you start your camera also?
Okay. Could you see this? You couldn't see this slide then?
No.
Okay. Well, I will start again. This is an A380, and here we have pointed out some parts of the air structure that are made of composite materials. We have all these places with CFRP, carbon fiber reinforced polymer, the section 19, the pressure bulkhead, the wing ribs. We have here even glare, which was a special development for this model, for the A380, which is what is known as a fiber metal laminate, an FML, which combines glass fiber plies with aluminum plies. And for instance, in this other graph that we see on the right, we have the consumption as aircrafts evolve along the past decades. They are lighter and lighter, and they are able to consume less fuel. They are lighter, and also the engines are more efficient. But the increasing amount of composite materials is plays also an important effect. I will speed up a little bit. Well, we have different types of composite materials depending on the matrix type and depending on the reinforcement type. But I will mostly focus on this presentation on the polymer matrix reinforced composites. Reinforced with ceramic fibers like carbon fibers or glass fibers, and even polymer fibers like Kevlar, polyethylene, polyamide, etc., etc. But the most common ones are CFRP and GFRP, carbon and glass fibers. One more slide about a bit of context of this use of composite materials and on history. We have composite materials used quite a lot on the ancient times, but these were natural composite materials like adobe. And in the late 90s, in the late 90s, the 20th century, we have the synthetic composite materials with these carbon fibers, glass fibers, Kevlar fibers, etc., etc. And we see that this use of composite materials has increased also due to the incorporation of these synthetic composite materials. And now let's move on to the modeling part, to the numerical part. And it is, my first question is, why modeling composites is complex? Why is more complex to analyze or to understand how a piece of carbon fiber ply deforms or breaks apart compared to a piece of steel, for instance? There are two main reasons for this. One is the heterogeneity, which means that these materials are composites. They are made of two separate phases. And the second one is anisotropy. And what does anisotropy means? Well, if we take our ply, this ply that we see here on the left, this will be a very small piece of a ply, a unit cell of a ply, and we stretch it in the fiber direction, we will have a stiff response, a stiff stress strain curve. However, if we stretch it in the transverse direction, this stiffness will be much lower. Why? Well, in this case, it's very easy to see that we have fibers reinforcing the longitudinal direction, the green direction, but on the transverse direction, we don't have the fibers reinforcing that direction. So it's basically the matrix is controlling the stiffness in that direction. So that's why we have such low stiffness. And this is what we call the longitudinal stiffness or the transverse stiffness. So anisotropy means that the mechanical properties, not only stiffness, but also strengths or fracture, all these properties, all these mechanical properties depend on the direction. And for instance, if we look at these strengths, here we have what happens if we take this unit cell, this small volume of a ply, and we apply longitudinal tension, longitudinal compression, transverse tension, and transverse compression. As we can see, these two first values that we see here on the right, xt, is the strength, tensile strength in the x direction, in the longitudinal direction, and this is the xc longitudinal compressive strength in the longitudinal direction. We can see that these values are much higher, are about 1,500, 2,000 megapascals. And if we apply tension and compression in the transverse direction, the values that we get are much lower, are a lot smaller. So this is one more effect of this anisotropy. And this is for a unidirectional ply. If you have a woven or you have a random distribution of fibers, you may have some sort of more isotropic or orthotropic behavior. And apart from that, we see that even the fracture mechanisms, the fracture planes that we see are different. They depend on the load that we apply. So yeah, this makes these composite materials quite complex, or at least more complex than other more homogeneous isotropic materials. So the next thing I want to explain is how are these materials organized or structured. If we look at one ply of composite material, let's say we have a unidirectional ply, or let's say we have a woven. Let's say we have a woven. We have some thickness of this ply, typically below 1 millimeter, 1/10 to 10ths of a millimeter, depending on the material we have. For wovens, these typically are thicker, around 0.4, 0.5, etc. And we can have plies with many different configurations, unidirectional fibers, randomly oriented, or woven plies, and some more even. If we take several plies and we stack them together, we make a laminate, and a laminate typically is a few millimeters thick. And typically we have multi-directional laminates. We take plies. In general, is the same type of ply, but we put it in different directions, and that's why we call it a multi-directional laminate. So we have this first hierarchical level, but also if we look closely at one of these plies, we will see the microstructure. This microstructure here corresponds to a unidirectional ply. And as we said before, here we have fibers, reinforcement, and the matrix. And as I said before as well, this reinforcement could be fibers or could be anything else like particles. So all these scales are related to each other. We can obtain information from all of these scales and use that information in the next scale, or at least we can use that information to understand why these materials behave as they do. Well, the freedom, the design freedom that we have when selecting composite materials, when designing composite parts is huge because we have many types of fibers among which we can choose, like we said, carbon fibers, glass fibers, but in between, inside carbon fibers, we have plenty of other subtypes of carbon fibers. We have high modulus, high strength, intermediate modulus, etc., etc. We have many matrix types. Just looking at polymers, we have many different polymer types that are used as matrices. For instance, now more and more thermoplastics are coming into play. And architectures as well. We said unidirectional plies, but we have also woven plies, we have braided plies, 2D wovens, 3D wovens. We have a lot among we can choose. And apart from that, we also have the stacking sequence when we put one ply on top of the other. All these directions and how many plies and what is the order, the stacking sequence that we have. In the end, we have an almost infinite number of combinations that we can come up with. So there is a huge design space. And finding the optimal choice, the optimal combination is not an easy task. And that's why numerical simulation has become so important for these specific materials. So if we look at the practical part, we will go to the industry, we go to Airbus or to Boeing or any other company fabricating, manufacturing products with composite materials. We will find this type of certification pyramid, and this pyramid is made of experimental tests, are experimental campaigns. And as you may know, experimental campaigns are very, very costly. And the aim of these will be the results of an experimental test at the coupon level. These are some open hole compression tests. And this will be down there. And what we want to do is to try to replace part of these experimental campaigns with numerical simulations. And that's why we have this blue or purple section in this pyramid. Because that's the goal, to try to replace, to try to predict how the material is going to behave in our computer, which is a lot cheaper. So the aim of this is to reduce, in the end, time and cost to the industry. Okay, let's go to the multiscale modeling part. What is this multiscale? Well, I guess many of you will may have heard of it if you're working with composite materials. But in a sense, the multiscale strategy aims at characterizing the whole material. And where does it start? It all starts with the experimental characterization of the constituents. So we measure in the lab, or we obtain from the literature the mechanical properties of the fiber, the matrix, and the interface. We try to find all that. And then we put these properties into microscale models, what we call computational micromechanics. In these models, we explicitly represent the constituents. We represent the fibers, the matrix, and the interfaces. From these models, we obtain what we call the homogenized properties. The homogenized properties of the ply. For instance, this model would be for a unidirectional ply. From these models, as we said, we obtain the ply properties, and we pass these properties to mesoscale models. These mesoscale models homogenized already the ply. So we don't have fibers. We cannot see these little circles anymore. We have individual plies. And typically, we also represent the interply region, the bonding between one ply and the one at the bottom, and the plies that are next to this. So we have this red red lines here, red planes here, which represent this interply. And this interply will be able to capture, with this interply, we'll be able to capture delamination, which is another mechanism that we will talk about it a bit later. And finally, you can think of it. You can think of these models as, well, they are great. They homogenize the fibers, the reinforcement, etc., etc. But what if we have a large panel, a large component, and it has 20 or 40 or 100 plies? This is what happens in a fuselage. It has hundreds of plies. Well, in that case, we need to simplify even more the geometry, simplify the model, and we use computational macromechanics or macroscale models. In this case, we do not represent explicitly every ply. We don't represent the plies. They are only represented as integration points. So we use shell elements, flat elements, to represent the whole laminate. This is valid, or this is accurate. This is still accurate as long as the thickness is very small compared to the size of the component. And this is the basics of the multiscale. This is called bottom-up multiscale. Let's take a closer look at microscale, because it's good to understand what we get from microscale, and then later we will focus on the mesoscale. So the microscale, we have the ply. We know that we have a ply. We stack these plies together, and from these plies we get we can look at the microstructure. So the idea, or what I like to think about micromechanics, is that we can use it to, first of all, to understand how the material behaves, how the constituents behave. Then we can use it to predict how this material is going to behave under some specific loads. What type of failure are we going to see? What damage mechanism will we observe? And finally, we can use it to even to design materials, design architectures that doesn't exist yet. So this is what and this is the loop, the cycle that I like to speak of from this perspective. Understanding first, then we will be able to predict, and finally we will be able to design. We can predict something that doesn't exist yet, and we can optimize, etc., etc. What type of models do we find in micromechanics? Well, one of the most well-known or most found models in the literature are the RVEs. What's an RVE? It's a representative volume element. And typically it's a periodic representative volume element. These volume elements represent a small piece of the microstructure, and to be able to use such a small piece of volume, we use periodic boundary conditions. So this PVC that you see down here, it's that periodic boundary conditions. The models, the advantages of these models is that they are small. They can use pretty small representative volume elements. And one of the features of micromechanical models is that they have the geometry is very detailed. We can see every fiber, and not only that, but we have the interface as well if we want to capture the bonding between the fiber and the matrix. However, these models are not convenient. Actually, we cannot trust the results of this model once we have fracture and damage propagation. So let's say we apply some transverse tension on this model. When we see that we have some cracking, we have some damage, whatever we see afterwards, after that point, we cannot trust it. We should go for a different type of model. So these models are feasible to analyze the elastic deformation and the initiation of damage, but not the fracture process, the damage evolution. What do we use if we want to analyze that fracture processes? Well, we have to use embedded cell models. In these models, we don't have a small piece of the material represented. We have all of the material. For instance, it would be a micro test, a few millimeters long, a very small specimen, and it's a 3-point bending test. And how do we represent damage here? Well, what we do is we are going to put a cell of the material embedded into the model. The rest, all this yellowish color, is it's a homogenized material, a homogenized version of the ply. This ROI is the region of interest. So with this, the disadvantage of these models is that they are large, they have to be large. And the other, the advantage is that we have real boundary conditions. So, well, these models are good to capture fracture, but are more costly, are more computationally expensive. And a few more examples of these type of models that we can find. Well, we can find RVEs, 2D RVEs. For instance, this is from part of my work on non-circular fibers to see how they fail, to see what is the influence on the elastic properties. But we can find other RVEs, for instance, to analyze longitudinal properties. This is an RVE for 2 RVEs for to analyze fiber kinking, to analyze longitudinal compressive response of unidirectional plies. And on the other hand, some embedded cell models. This could be one embedded cell model. We have the microstructure as a strip, a horizontal strip here, and we see a crack that is propagating across this microstructure. And what we see up here on top is what is called the R curve, the curve that summarizes the fracture process, the energy dissipated in the end, like 50 joules per square meter. This will be the fracture energy of this material. Okay, let's move on. We've seen some examples. We've seen some things about the micro scale, about computational micromechanics. What can we do? What do we need to represent these models? And now we move on to the mesoscale. Why microscale models are important for the mesoscale? Well, on one hand, these models help us to understand what happens at the mesoscale. We can see fracture mechanisms a lot better than at the mesoscale. And we can obtain the properties of the ply and pass these properties to mesoscale models. We have two big groups of properties. We can divide them into elastic properties and every other property that has to do with fracture. We will see a bit more in the next slides. So going into the mesoscale, we also have a few different types of models, of families of models, we could say. On one hand, we have the homogenized plies, which are probably the most widely used. And in these models, what we have is that we don't have fibers anymore. As we said before, we homogenize the microstructure and we represent every ply with an element, we could say, with a finite element, as we see here in blue. We have 4 plies, we have 4 elements, and we also have the interply. So in between the elements, we can define a cohesive zone model. How do we define this cohesive zone model? Well, there are mainly two ways, at least in ABAQUS. Depending on the software, you may find variations, but it's in the end, it's the same. You have two options. One is to use cohesive elements, this white thing that you see in between the blue elements are cohesive elements, are other elements that are very, very thin. And they are used to capture delamination, or we can use cohesive surfaces. We can use a contact, sort of a contact, with some strength as well, some strength and fracture energies. These models are still very detailed because we model, we draw every ply. The plies are homogenized, and also the interplies are modeled, as we said. So, for instance, here on the left, here we see another example of a model. We can see the different plies on different colors, and in this case, there is one more thing that you cannot see. We cannot see explicitly, but we can guess from the fracture that we see here. We see some sort of strips of elements. And this is because the mesh is aligned in this case, and you can have some type of cracks following the fiber direction. And well, this is another example. In this case, we are looking at some stress field on one of the plies. So we can run actually very detailed analysis using mesoscale models. There is another family of mesoscale models, and are those dedicated to fabrics, to woven plies. Because in this case, actually these models are somewhere in between the microscale and the mesoscale, because we don't model the plies in a homogeneous. We don't homogenize the plies. We homogenize the yarns, the weft. So we don't have fibers, but we still have yarns. So these plies are still heterogeneous because every ply is made of yarns, which are like a unidirectional ply, and the matrix, the polymer resin, for instance. These are used to analyze what is the deformation mechanisms, damage mechanisms into the woven ply. However, these are very complex. These models are very complex because of the geometry. We may have a lot of intersections, interpenetrations of one yarn with the other yarn, especially if we want to have a very high volume fraction of yarns. Because in the end here we have all the yarns are put together, are compressed together, and that's very difficult to model that geometry. So here I have a couple of references. This is from Verkamp et al. From 2018. He did his PhD at the Imperial College, and he developed some models and some framework to create these models. And the other resource that I want to tell you about is TextGen, which is a free software. I don't remember right now the university that created and provides this software, but you can download it and install it, and you will be able to at least to get the initial geometry to make a woven ply. Later on, you may have to tweak it, to compress it, etc., etc. But well, these are some of the resources I wanted to share with you. And now I will still focus on the homogenized plies. Because in fact, once we know very well how the textile, the woven plies behave, we can homogenize them and use these same strategies, these same modeling techniques that we see on the left. And I will start talking about these techniques. So the inputs that we required in our mesoscale models are the elastic properties of the ply. We can get these properties from the microscale, or we can go to the literature. If we are lucky and we're using a popular material system, we may find these properties. At least the elastic properties are the easiest to find. We also need the ply thickness, and this is, we can measure it in the lab, or we can get it from the manufacturer. We also need the laminate stacking sequence, and this is something that we may know already, maybe if from a standard experimental method, or we have designed some stacking sequence. So we have the details of all the plies. And from every ply, we need the fracture properties. We need two types of properties. Fracture properties are divided into two. One is properties for damage initiation, and the other are properties for damage evolution. We will see later what's this in detail. And we also need the properties of the interplies, the properties of the bonding between adjacent plies. And this is what we call interlaminar properties. This is what is going to be the lamination later. And we need the same for these ones. We need damage initiation and damage evolution. So let's go ahead. Let's see in some more detail what are these details on mesomechanics. First, we will look at ply modeling. So this is what we call intralaminar damage. And next, we will see what is interlaminar modeling to model delamination, interlaminar or interlaminar damage as well. So let's take a look at this. So we will be focusing on this lower side of the slide in this part. And first of all, to understand how damage works, we need to start with with damage initiation. And a synonym for damage initiation is failure. When does the material start to fail? Well, this is given us by what we call failure criteria. What is a failure criteria? Well, in a sense, it's a function, like a mathematical function. In this function, we provide the stress state or strains, depends, and the material properties, typically the strengths. And this function is going to give us if the material fails or not. So this function is going to tell us, yes, the material failed, or no, the material hasn't failed. This is all what a failure criterion is. If we look at a ply, we have some coordinate system. This is called the global coordinate system. But when we look at a ply, in general, we want to have the local coordinate system, especially when we have aligned fibers, or when we have a woven in which we have the direction of the warp, for instance. It would be the one direction. So that's why we have this 1, 2, 3. 1 is the fiber direction, 2 is the transverse direction, and 3 is the out of plane, which is not very commonly used for failure criteria. So this is why we will see 1, 2, and 3 a lot from now on. As we said before, well, in case of unidirectional plies, they are very heterogeneous and very anisotropic. In fact, if we take a look at some of these failure modes, like pure longitudinal tension, pure transverse tension. If we take a look at the values that we get, well, these are very similar values as we saw before in the graph, but here we have them in a table. But the idea is that we have very different strengths depending on the direction and also on the sign. If it's tensile, or if it is compressive, we have still different strength values. If we take a look at some failure criteria, for instance, one of the most typical ones, one of the easiest to understand as well, is maximum stress. So in this case, we compare every stress component with the strength in this direction. This is an uncoupled failure criteria. Uncoupled because doesn't matter what we do in the one direction to evaluate what happens in the two direction. We compare every stress component independently. If it's tension, we compare it with the tensile strength. If it's compression, we compare it with the compressive strength. And the same for the transverse direction. And we have also the shear independently evaluated. So if we take a look at these failure criteria, what we have is, if we take a look at, and we only have sigma 1 and sigma 2, what we have is something like this. We have straight lines, horizontal and vertical lines, because are completely independent. The next criterion that we can see is the maximum strain, which is somehow similar, but in this case, we compare the strain to failure, the strain at which the material fails on each direction. So what we get is similar, but we still have some straight lines, but they have some tilt, some inclination because of the Poisson effect. We have to evaluate. We can, if we take a look at, if we take these equations and we plug the Hooke's laws, then we will get these lines, and you will see what is the slope of these lines, which depends on the Poisson ratio mostly. What else do we have? Well, we have something more now dedicated to composite materials. It's one of the first failure criterion for composite materials, and it's the Psi-Hill. Psi-Hill is a unique expression, so we have some coupled effects. We don't have to evaluate separately longitudinal, transverse, tension, compression. No, we don't do that. We put all this in a single expression, and if this value is lower than 1, the material hasn't failed. If it's equal to 1, the material fails. What's the shape of this Psi-Hill criterion? Well, it's more of like an ellipse. If you take a look here and apply some calculus, some maths here, you will see that is an ellipse. This is the Psi-Hill criterion without any shear. What happens if we apply some shear? If we apply some shear, this ellipse becomes smaller. If we apply shear, the maximum tensile strength that we can apply is lower, and the same for the others. And there is one more. I made it smaller just to improve the visualization. And another failure criteria that we have, classic failure criterion, is the Psi-Wu criterion. This criterion, again, is also a single line, a single expression. We have these variables. Well, these are constants because they depend on the material properties, but we have these other parameters. And if we look at these, and if we evaluate this function, the shape that we get is something like that. Similar to Psi-Hill, but it goes the other way when we have sigma 1 and sigma 2. And if we have some shear, it is as with the Psi-Hill. This ellipse is smaller. So these are some of the traditional failure criteria for composites even. But I don't recommend using these failure criteria very much. Why? Well, mainly because we don't know how is the material failing or what is the damage mode that we have. They are not telling us anything of this. What are other advanced criteria for composites? Well, one of the older ones is the hashing criterion. It considers different failure modes, and it also couples some stress components. Other criterion is Budiansky criterion. This one was focused on longitudinal compression. He developed what is known as fiber kinking theory. Then we have the Puck criterion, and this one is very important because it's the basis for the most sophisticated criterion that we can find nowadays. And this one was focused on the transverse failure, especially transverse compression of the plies, because it combines transverse compression with shears. It's able to compute the fracture plane, etc., etc. So it's really worth it to look into this reference, into this paper. And finally, the last criteria or family of criteria that I want to show is the LARC criterion, which was developed by NASA in 2003, 4, and 5. That's why it has this name, LARCO 3, LARCO 4, LARCO 5. LARC is Langley Research Center, NASA. And this criteria takes all or the most important features of previous criteria. It takes the fiber kinking theory, it takes Puck criterion, and it embeds a few more details into these. So, for instance, it considers nonlinear shear, which affects fiber kinking theory. It takes into account pressure dependency of the resin. Polymers are very pressure dependent. And a few more details. Here you have also the references to if you want to dive deeper into these criteria. And how does it translate into the numerical part? How do we take these failure criteria? Well, for instance, in ABAQUS, we have hashing criterion. What is hashing criterion? Well, hashing criterion is made of these 4 equations, and we have multiple failure modes, 4 different multiple failure modes: longitudinal tension, compression, transverse tension, and transverse compression. It requires a 2D stress state, so it's only compatible with planar elements, with shell elements or membrane elements, and it's nice. It's good to use when we have unidirectional plies. However, this is not the case when we have woven plies, for instance. This is not very appropriate. This transverse compression and transverse and longitudinal compression doesn't work as well. So to recover from that, we have the ABQ ply fabric criterion, and this criterion is not into ABAQUS. This criterion is an built-in material model. You can look on the internet for this and you will find the documentation and how to use it. But in a sense, it's like a maximum stress criterion, but it allows to include non-linear shear, for instance, which is very important in woven plies. We have a yield function for shear. It's still a 2D stress state, which might be even better for modeling. And it's very useful for woven plies. And what I was saying is that it's not only a failure criterion, but it also includes damage evolution, which is very important if we want to analyze, if we want to run a progressive damage analysis. Okay, let's go one step further. We have seen failure criteria, and we know that we need the elastic properties of the ply, and we need the fracture properties. On the one hand, we have the failure properties, which are strength and the failure criteria that we want. And this will give us this will tell us when the material fails. So when the material reaches this point, it has failed. This blue color is damage initiation. But what happens next if we keep pushing, if we keep stretching our ply? Well, we will have some softening. And this softening is what we call damage evolution. And we need more properties for this damage evolution, which are typically fracture energies or toughnesses. It's not exactly the same. Fracture energies are G's. Toughnesses are typically stress intensity factors, critical stress intensity factors, K. So in the end, for instance, for a ply, for the in-plane properties of the ply, we need all these properties, these elastic properties in yellow, these strengths in blue, and these fracture energies, these properties for damage evolution in purple. We have 1 plus, 1 minus for longitudinal tension, longitudinal compression, transverse tension, transverse compression, and shear, G6, in-plane shear. When we want to model damage in a composite ply, we have two big families of damage models, what we call continuum damage mechanics, CDM, or discrete damage mechanics. What is the main difference? Well, main difference is that when we have CDM, damage is smeared inside the elements. We cannot see cracks, actually, unless we delete elements. And when we have discrete damage mechanics, we do have cracks. We have a separation, a real separation. Cracks are visible. I will be focusing on CDM for intra-ply damage. In CDM, damage is represented inside a continuum. We have damage evolution as the softening law. We have some mesh effects, and we can avoid this if we know how to. We need to know some of the fundamentals of CDM. And well, we do not see cracks, but as I was saying before, we can delete or remove elements to have some sort of cracks. So in a sense, how does it work? Well, we have our piece of material, our piece of ply. We apply some strain. We reach the failure criteria, and from that point on, we have softening. The stress decreases, so we start having this damage. At some point, the stress goes to zero, and we may delete the element at that point. We can erode the element. And on the other hand, well, we have discrete damage mechanics. And how do they work? Well, if we take a look, for instance, at XFEM, which is one of these techniques of DTM, this technique is mesh independent or wildly independent, and crack orientation is calculated in runtime. So if we take a closer look at this image here, what we see is that this crack goes through the elements. It's amazing, but I started working with ABAQUS and with numerical models without this technique. This technique didn't exist yet, and when I saw this was blowing my mind. But you can see a crack through the elements, and this crack is created at runtime. We don't introduce this crack before the analysis. So one more thing that we saw before, we have two types of damage. We have intralaminar damage inside the ply damage, which we can represent, for instance, here with a continuum damage mechanics model. In red, we have the elements that failed, the elements of the plies that failed. And we have interlaminar damage. We have delamination. So here, for instance, we have several plies, and we can see that eventually they separate from each other. This blue color was that delamination. Well, this is a bit more on interlaminar damage. We've already talked about this. We have different failure mechanisms, and interlaminar damage is what we call delamination. And in a sense, we have two, or we could say three damage modes. We have the opening mode when we separate two plies like that in the normal direction. The shear mode when we have a sliding, we have shear between them, or we can have a combination of these two. So I will take a brief look here at another example, another model, in which we have modeled this delamination by inserting in between these two plies This was a pre-crack. That's why we don't have red on the right. Where we have, so we have introduced in between these two plies cohesive elements. These cohesive elements are going to are attaching together, are bonding these two plies. However, when we apply some forces and these cohesive elements suffer some stresses, they are separated. They open up. They are opening. So this separates more and more, and this is what we call delamination. This is a cohesive zone model, and typically delamination is modeled through cohesive zone models. In this case, the cracks, we have to place them in advance. Well, in this case, we don't have a crack actually, but we have the interlaminar region. So we put elements, cohesive elements, in between two plies. And there are two ways in which we can model this, as we commented before. We may use cohesive elements, or we can use surfaces. We can use cohesive surfaces, like an interaction, like a contact between the two plies. Cohesive surfaces, for instance, are very useful when we have aligned meshes, and one of the plies has one type of mesh in one direction, and the next ply has the mesh in another direction. So the nodes do not match. So we have to use something that doesn't need elements, that doesn't need cohesive elements, and these are cohesive surfaces. And well, one more, delamination is a very important topic because it's a damage mode that is not easy to detect. It's not easy to find. In some cases, let's imagine we are on a plane, or we are looking at a panel, and some tool or bolt or some tool falls down onto this panel. If it's a heavy tool, if it has energy enough, it will provoke some delamination within the laminate, and we won't see this delamination easily unless we can use different non-destructive techniques, but it's already an important issue, and we want to understand how delamination appears, how it propagates, and how it affects the structural integrity of the structure of the panel, of the plate, of the stringer, whatever is the component. So delamination is a very big issue. How do we model delamination in some more detail? Well, we have, as we said before, we have two plies, for instance, here, and in these two plies, we have in between these two plies, we have the interlaminar region. In general, this interlaminar region is very, very thin. Could be a 0 thickness element. We can make that. If we look at this interlaminar element or cohesive element, and we look at the stress state that this element has, we have, since it's 2D, we have two types of stresses. We have normal stresses, which are perpendicular to the surface, to the element, and we have shear stresses. Of course, if we have a 3D model, we have shear stresses in one direction, for instance, this left-right direction, and we also have another direction which goes out of the screen. We have also failure criteria for this cohesive, for this interlaminar region. If we can use this failure criterion, this is called a quadratic stress failure criterion. It's like a maximum stress somehow, but we are adding up all the contributions. Like we have normal stress here, shear stress, and the other shear stress. And we add up all of them. These brackets here means that sigma n is only taken if it is positive, if it's a traction, if it's a tension load. If it's compression, we don't take it, it's 0. And in a sense, for the interlaminar region, these are the properties that we need. We need strength for each of these stress components. And we have also fracture energies. As before, this works as before. We have the elastic part first, Then we have damage initiation, which is this failure criterion, or any other could be, but this is one of the most common ones. And then we have evolution of the damage, of the delamination, of the separation of the element, of the cohesive element. And this is given by this GN, GS, GT. So now we have a sort of the big picture of everything. We know a bit of intralaminar damage, interlaminar damage, what kind of properties we need to model each feature, when do we need damage evolution, when do we need damage initiation? Well, depends on the analysis that we want to run. And now the question is, where do we obtain these properties from? Well, we need all these properties for the mesomechanical model. And some of these properties, especially for the ply, for the intralaminar damage, we can obtain them from micromechanics. For instance, elastic properties, strengths, we can get fairly good estimates from micromechanics. For fracture, it's not so easy, but we can still try and see in the literature some models that have been able to get those properties. But what if we don't find these properties, or we don't want, or we don't have these micromechanical models? How can we measure these properties in case we don't find them in the literature? Well, let's start with delamination. How do we characterize experimentally these properties? I will be focusing in delamination, I will be focusing on fracture properties, because actually strength properties are not so determinant, are not so important here, even though if you have any question about this, we can talk a bit later on this. For instance, if we want to characterize the fracture energy in mode 1, in the opening mode, well, we use the very popular DCB test, double cantilever beam. This is the standard for this DCB. If we want to characterize shear, which is shear mode or mode 2 delamination, we can use the 3-point bending test. We can even use the 4-point bending test as well, but well, this is the standard. This one that we see here, and the 3-point bending test is like this. We have we use bending. We apply the load in the middle, in the midspan of the coupon, and we need to have a pre-crack. Of course, in the DCB as well, we need pre-cracks for fracture characterization. And the last one wasn't here before because I didn't want to extend very much or to mix too many topics at once. And this is the mixed mode ratio, and it's a parameter. It's a property that is going to account for the for mixed mode delamination. So this one is this ASTM, and one way in which we can test not pure mode 1 nor pure mode 2 is to test some mixed mode in between. And actually with this we can test any mode mixity that we want. Is this MMB test. This requires a special fixture, but it's very versatile, and you can get any mode mixity in between and see how is the transition between pure mode 1 and pure mode 2. So this is all the most relevant characterization techniques for delamination. And well, as I said before, we will see if you want, we can talk about strengths later on this. And we have the intralaminar, the ply properties. So we have elastic properties, strengths, fracture energies. The first test that actually can be used to characterize most of the properties, all the tensile properties, not the fractures, but the tensile strength and transverse tensile strength, is this one, is the D3039, and it's a uniaxial test with a long coupon. Of course, depending on the orientation of the plies, this laminate, all the plies are in the same direction, but depending on the orientation, if they are at 0 degrees, we will evaluate longitudinal properties. If they are at 90 degrees, we will evaluate transverse properties. There are some issues if we want to analyze YT, the transverse tensile strength. If we do it this way, we may get lower bounds, low values. But, well, this is something that you will realize, or you will already know if you have worked with this type of test. Then we have this other standard for the shear characterization for the elastic, only the elastic properties, the elastic modulus, which is by applying tension on a plus minus 45 specimen. This is the standard. If we want to analyze the compressive properties, then we have something similar to the uniaxial tension, but we apply uniaxial compression in a shorter specimen. That's why we have these tabs here, and the free gauge is shorter because we want to avoid buckling of the specimen. What about shear strength? Well, for shear strength, we can use, or at least the standard is this one, which is the short beam test. And this is what the industry tells us to do if we want to characterize this shear strength. So it's like a 3-point bending test, but it's so short that bending will be negligible. So all we have is shear. And now we go to the complex, the most difficult part, and it's to analyze fracture. What if we want to analyze the fracture energy in the longitudinal direction in tension? So this is G1 plus is like G1T, like tension. This plus is the same as tension. For this, there is no standard, at least for now, or to my best knowledge, I don't know any standard for this one. There are some publications, and this is one of them, that pretends to become a standard, and I think it could be, and is to use a compact tension test to obtain this value, this fracture energy in the longitudinal direction. With some assumptions, it's not a pure 0-degree laminate. It has 90-degree plies as well. So this is a reference that you can use and put into practice if you want to measure this property. For the one in compression, longitudinal compression, well, we have another reference here. There is no standard either, and this is one test or one set of tests in which Catalanotti and colleagues, I think it was Camaño as well, designed some coupons and some technique, some strategy with different sizes of this coupon to extract the fracture energy under longitudinal compression. For the G2 plus, well, we could use the standard that we saw before. We can use the double cantilever beam and plug that value here. This we can discuss, somebody could argue about this, but this is something that is that appears as reasonable nowadays, because there is no better way to have an estimate of this property inside the ply. We can use the delamination, the interply property. And for G6, it's also the same. We can use the 3-point bending test, and we can take those values and put it here as well. So these are all the standards or experimental tests that we can use to characterize most of the properties of the ply. And this is applicable, if I'm not wrong, I've thought about it, this could be applicable with some adaptations to woven plies as well. Okay, so now I'm a bit late. I'm 10 minutes late. And now I go to the hands-on example in ABAQUS to show you some of the things that we have seen already.
Can you turn on your camera, please? Yes.
My camera, yeah, sure.
Yes.
It wasn't turned on. Okay. Can you see the screen?
Yes, yes.
Okay. So I'm in ABAQUS now, and what I'm going to do is to use a model that I already have because we don't have much time, So what I'm going to file, run a script. The model that I'm going to use, I'm going to generate it on the fly. So I will go to run a script. And this is something I like very much doing in ABAQUS because we can modify whatever we need very fast, and we can generate our models with new modifications very, very fast. We can. I will use a Python script to generate the model, and here it is. So what I have done is use a Python script that has told ABAQUS how to create this model, how to create all the parts. We have this part which is our composite component, and we have the other part which is a pin, a solid, a rigid solid. So I will go to the assembly, and the model that we have is that it's a fixture of a pin. So we're going to apply on this face here a tensile load, and the pin is going to be fixed. So we will have here the force, and we will have a contact between the rigid solid and our composite part. And there is where we will have the highest stresses. I will show the mesh that we have. Well, you can see that it's a very coarse mesh, a very big elements, but like this, we can solve it here faster. One more thing we can see here is that we have 2 plies, also only 2 plies, but it's also to make it faster. But we have different, we could have different materials on each of the plies. In this case, it's the same material, but what we have are different orientations, different fiber orientations on the plies. Let's solve this model. I will go down here to jobs, submit. Okay. It will take a few seconds, but it will be submitted. I will go to the materials part. So here we have the only material that we have in our model, this IM78551. Okay, there it is. And in this material, for this model right now, we only have elastic properties, these properties that we see down here. In fact, we have here properties in the 3 direction, and this is something that we don't really need. We need these properties if we use solid elements, if we use 3D elements, volumetric elements. So we need properties in the 3rd direction, through the thickness direction. But in the end, hashing is not going to use this 3rd dimension. So we cannot use hashing with solid elements. What we have here in our model, let's go to the part. This, I will plot the elements. These elements look like solids because they have some thickness. But in a sense, these are continuum shell elements. And this is a special feature, a special type of elements that look like solids. They have some thickness, but they behave like shell elements. So we don't have stresses in the 3rd direction. We don't have stresses or strains in this 3rd direction. So that is why if we go to the material, all these properties in the 3rd direction are not being used. And that's why we can use hashing. So we have all these strengths that hashing needs: longitudinal strength, longitudinal tensile strength, longitudinal compressive strength, and the same for the transverse and shear strengths. But we don't have anything else. We only have damage initiation. We only have strengths. So we're going to use hashing this time as a failure criteria, only failure. So if we go to the model that has finished already, let's see what we have. Okay, I will show the shadow. Okay. If we go to our model now, we now have some stresses, but let's look at the failure criterion. So we come here, and instead of S, which is stress, I would look at hashing fiber tension, for instance. This is hashing FT. This is fiber tension. If we take a look at these, I will change one more thing here. I will come to, here to contour options. And I want to see these results on the element. I don't want to see these bands of colors. I don't want to ABAQUS to plot interpolated values. Oh, I have to modify something else. Yeah, I have to come to results, section points. I want to see the results only at the bottom of the ply. That is something I had to do. I cannot plot the top and bottom at the same time with quilt. So I will say bottom. Okay. And now I will say quilt, apply. And now we have one value on each element. So for this failure criterion, what we have is 0.22, the maximum value. So under fiber tension, this composite, this part hasn't failed yet. Let's take a look at another one. Let's say we have matrix tension, which is the weakest matrix tension. And in this case, we have a value of 16, almost 16. This means that under this load that we have now, the material has already failed. The material would have failed already. So this is how we can use hashing as a failure criterion. We don't have still damage evolution. We don't have that in this model. How can we get that? Let's go to the next example that I want to show you. And in this case, I will open it so we don't spend time in the solving process. And the next example that I want to show is, yeah, here it is. I will go to this one. In this example, I will plot some deformation that we get. And let's do the same. I will go to hashing MT, matrix tension. And in this case, this criterion only goes up to 1. So in this case, if we go to see the properties that we have specified, in this case, we have introduced the fracture properties, the fracture energies. So we do have softening of the material. And this is what we see here. We see elements in red that have failed because of this. And what we do have now, in addition, is that we have a damage variable. We have the damage variable, for instance, for matrix tension. And this variable is also has also some value. It's 0 where we don't have damage, and it is between 0 and 1 where we do have damage. So this is one case, one of the plies. I will show only one ply, for instance. I will come here to the display group, and I want to display only ply 1. Okay, like this, better like this. If we animate it and we see what is going on, so what we see is that at some point the part will break here. We will have damage on that area. And that is what this damage variable is telling us. If we look at another ply, I can actually make another viewport and see both plies. So if we look at another ply, damage matrix tension, and I ask for the ply number 2, then, okay, let's link these viewports and let's see what we get at the same time. Maybe I can, yeah. So as load increases and stretching increases, we have some damage, and we have damage on the same area. Even though it's not exactly the same, we have damage on the same area. This is the point on which both plies are going to break apart. What else do we have in this model? Well, we have something very interesting in this model. That is, I will uncouple these, and I will Where is it? Okay. I will show in this model, what we also have is I will plot everything. And when I zoom in, we have this interlaminar region in between. These are cohesive elements, and these are going to capture delamination as well. So let's see that. How do we visualize those elements and the delamination? The variable that we have in this case is the damage of these cohesive elements is this SDEC variable, which is the stiffness degradation variable. And we don't see anything because these elements are behind, are in between. So what we can do is to apply the translucency to make all the model transparent somehow. Or I will undo that. What we can do instead is to only show the interply elements. So I have them in a set, and here they are. So I hide the rest of the elements. And I think I can move this to this side, move this downwards. So now it's a bit bigger. Yeah, much better. So now we can do as we did before. Let's play them together and see from the beginning what is happening. So we barely see any deformation yet. And at some point we have damage, and we also have delamination, not only in this area, but also around on the surroundings. We also have some delamination, and that keeps increasing as we move farther. And this is what we have. For visualization, there is something we can do if we want to remove the elements. If in case we want to show some animation or in some presentation or anywhere else in a conference or something like that, is that we can delete the elements, and we can do this coming here to fill output dialog and say status variable. We can use a status variable and say, for instance, the SDEC variable. So we can delete the cohesive elements that are very damaged. So let's say we remove the elements with a value of SDEC above 0.99. If we do it like that, some elements have been deleted, and well, we can move it, and we can delete some more elements, and this may be helpful for some cases. To conclude, one last thing I wanted to show, I should have showed it before, is that this ply has some local orientation, has some fiber orientation. What is this orientation? We can plot it here with plot material orientation. And like this, we can see the orientation of this ply. In blue is the fiber direction. In yellow is the transverse direction. So this ply has fibers, is oriented in the 0 direction. We could hide that if we want to make it more clear. And this is how we can visualize this. And we can take advantage of this, for instance, to plot only the stresses in this direction. Go to S11, and these are the stresses in this direction. We can even plot the vectors in this direction. Okay, like that. So we only have the components in the fiber direction or in the transverse direction, etc., etc. And this is all what I wanted to show you today. Well, I think there were too many things to show. So I try to dive into some of them, like fracture, failure, but there are still many more details. We didn't go into most of the details, of course. But well, I guess you may have now some big picture of these modeling strategies for composites. Thank you.
Thank you, Dr. Miguel. It was indeed a wonderful presentation. Can we take 2-3 questions if you allow? And can you show the material properties of the last model?
In ABAQUS or?
In ABAQUS.
Yeah. The material properties for the last model. I have to run the script to see those properties. And this one is okay. So the material properties that we have are for the ply and for the interply. Which ones do you want to see?
For the delamination.
For the delamination. Okay. So for the
Supply.
interply, the most important properties for delamination are these ones, are the damage evolution properties. These energies are the most important ones. Because delamination is a fracture process. So the most important ones are these. It's a energy dominated process. It's not stress dominated. So how do we select these strengths? Because this was one of the questions that I left open. We can take these strengths from the ply properties. This is one option, to take the transverse tensile strength, the YT property, or the SL for shear. And this is how we use what we usually do. However, if we do it like that, and we want to use, I will close this for a second, and we want to use such big elements, then we will see that we have a problem, because if you compute the length of the fracture process zone, the characteristic length of the delamination process is going to be smaller than the elements. So we can tweak that, and the results won't change very much. Actually, won't change at all, almost. And we can tweak that, and we can reduce these strengths. That's why we have such low values for strength. Because when we reduce the strength, we are increasing artificially the length of the fracture process zone of the delamination process. So with these 20 megapascals, which is very small, what we have is that the length of the fracture process zone is bigger than the element, is around the element size with this value. So we are tweaking this for that. There is actually a paper on this. I didn't invent this. There is a paper from Turon and Davila, in which they explain this, how to make this, and they show some results, and they explain they explain that tweaking the strength of the delamination material, of the interply material, doesn't affect the propagation of delamination. So this is an advanced feature, we could say.
Can we take 1-2 questions if you have time?
Yeah, sure.
Okay. So there's one question. Sir, can you please guide what kind of mathematical foundation needed to start learning simulation modeling in mechanics?
Okay. Well, that's a very broad question.
Yes.
Well, that is completely independent of modeling composite materials or metal materials, or definitely if you're starting with numerical simulation, numerical modeling, don't start with composites. Start with some easy to understand material. Start with linear analysis, elastic materials, isotropic materials, and start always from the easiest you can do. You can find on the internet many tutorials to start working on that, but start with the easiest, and little by little add new features, add new stuff. Like, okay, I start with the beam element, I apply some tensile stress. There is a microphone open there.
I've shut it down.
Okay. So I recommend you to start from the very basics, and little by little go one step farther, and always try to understand what is going on. Actually, the mathematical part is not so important. What is important is to understand what is happening. And yes, you need some math for that, but not that much. But what you need is to grab what is going on behind the scenes. What happens? What is a node? What is an element? What is the relation between displacements and forces? Understand that you have degrees of freedom, these kind of things, and little by little go building on top of that. So I recommend you to go with simple models and always check the results you get. Simple models that you can solve by hand, like uniaxial tension, uniaxial compression, explain all these deformations that you get. So it's a long way, but it's a way that has to start sometime.
Okay, I will just take two more questions. One is from Qasim Zafar. Can you please turn on your mic?
Okay, I have one question. First of all, I would appreciate your very nice presentation on the ABAQUS modeling, particularly in the composite material. The second thing I want to ask about if I need to induce my own criteria through a user subroutine. For example, I have a user subroutine and I want to damage evolution on the basis of maximum stress or maximum principal stresses or maximum transverse stresses. It could be on the either side. And I want to induce this through user subroutines. So could you please guide me how I can, which user subroutine is more appropriate and how we can make it for the damage of the metals rather than composite?
Okay. Okay, your subroutines. This is the most advanced topic you can go when you're modeling. And if I guess you're starting to work with subroutines, or you have some experience with subroutines.
I have some experience with the subroutines like deflects and USDLF, but actually, what I found I am stuck on a problem with the metal additive manufacturing. I am working on the metal additive manufacturing, but there I can actually calculate the residual stresses. Perhaps when there is some cracks, I want to induce it. My own criteria that is entirely based on the maximum stresses. For example, for more detail, I want to add it to something. Usually, all the damage models or crack models, we need to develop a notched specimen, something like that, in extended finite element method or some. But in additive manufacturing, the cracks are arbitrary. They are small micro cracks, and the large cracks, they are spreading over the arbitrary position. So I want to make it realized through a user subroutine where there is a maximum stress. There might be some cracks. Either it is a micro crack or maybe the large crack. So that is actually my point. And how I can realize this through the simulation, maybe through user subroutine.
Yeah, that's so even before the subroutine, I guess you want to, since you have distributed cracks, what you may want to use are a continuum damage model, I guess. Because you will have tiny cracks, some other bigger cracks. So using discrete damage, using XFEM or using some phantom node method wouldn't be efficient. You would need tiny elements, or you would need, I'm not sure, but probably it would be an important issue, especially when you have many cracks. XFEM, for instance, works well when you have few cracks. You have 1, 2, 3 big cracks, but they do not interact because XFEM cannot merge two cracks. So that's one important limitation of XFEM. So you want to model smear damage inside the elements. So for the subroutines, I can recommend you a couple places that you may want to look at. They are not exactly for metals, but maybe you can get some ideas or some clarifications. One is a subroutine for damage of composites, which is open, and is on GitHub, and it's from NASA. It was developed by some colleagues there at NASA, and it's called CompDam. I think I can maybe put it in the chat. CompDam. Look for that on GitHub. It's not a single subroutine, it's actually a framework. So what I think that you may find is that the people who have done this, Frank Leone, Andrew Bergen, Carlos Davila, all these are awesome scientists and researchers, and maybe you can get some ideas on the different failure mechanisms that they introduce, that they have defined. Maybe in any of them you may find something useful or some inspiration for you. And the other one is not a subroutine itself, but it's a paper or a PhD dissertation from Miami. I think there is a paper from Miami and Davila, maybe. And in this paper, he explains very, very well the mathematical foundations, the algebra below these damage models to make them work, actually. And the subroutine that you might be looking for is probably a VUMAT, because since you have damage, you may want to run this in explicit to avoid convergence problems and all that, I guess. But this is, I guess, something that you already know. So I guess these resources might be useful.
Thank you so much for all these suggestions. I really thankful for it. Anyway,
okay, I have a question that does these models account for the bending also, or
yes, bending.
like if there's no symmetry in the composite, then there are bending terms.
Yeah, if you have, in this case, it's mostly in plane, but if it were curved, the geometry, or if you have bending loads or out of plane loads, then you will have bending. For bending, there are two important things to take into account. In the end, bending, when we apply bending on a laminate, it turns into in-plane loads. You have for instance, from classic theory, you have a linear strain profile through the thickness. So on the bottom and top faces, you have the highest strain values, and this is what the failure criteria or the material model is going to take. Is going to look at the stresses or strains at that point, at that height through the thickness. So in the end, all bending is a macro mechanical deformation. So this is one thing. In the end, you will have in-plane loads. And the other thing is, in some cases, you may not capture bending, but not for composites, but for any other material. And this is because bending depends a lot, or capturing bending depends on the element type that we choose. If we use shell elements or these continuum shell elements, these type of elements have been designed for bending, are intended to capture bending. But if we, instead of using this continuum shell here, I use a solid element with reduced integration, and I only have one or two elements through the thickness direction, then if I recall from the other question, somebody who wanted to start in simulation, then you will get something very strange. Then you will get that your structure hasn't got any stiffness, any bending stiffness. If you use reduce integration elements with bending, you will see hourglass, you will see lack of bending stiffness, and the opposite. If you use full integration solid elements, you will have shear locking, something called shear locking, and this means that these elements are not going to deform, so it will be extremely stiff. So that's not realistic, and these numerical artifices is something that we need to be aware of, because otherwise we might be trusting our results and we are making this big mistake. So in the end, bending is take care of the elements that you take and make sure that the stresses that you get in plane are realistic, but they should be if you have chosen the right elements.
One more question. What is the best technique or procedure to model the 3D composites?
Okay, 3D composites. You mean I will I want to a bit more of context. 3D composites like 3D woven or
Yeah, 3D
or
woven. Yes, woven.
okay. 3D woven. I have to say I don't have much experience on this. What I know is from conferences or from people I have watched. For instance, I think I maybe can recommend one another reference. I don't know if by this name. Yes. I'm not sure if this is the last name, Munoz and Gonzalez. This is a reference for a former colleague who worked with some combination of homogenized plies with some trying to model the 3D weft or 3D yarns.
Binding yarn. Binding yarn.
Using beam elements or truss elements. I'm not sure of them, but there are some combinations. In general, this type of materials are so new, are so fancy, we could say, that there isn't any standard. There isn't any well, as far as I know, there isn't any clear research line to go and to use this model whenever you want, because it will work. No, there are actually many different families of models. You can go with the fully detailed analysis, but then you're limited to a small unit cell or volume element. Go to TextGen, try to find the geometry and plug it into ABAQUS, and you will have to fight with the model a lot. But I think for a bigger component, a few centimeters long component, you will have to homogenize that. You may have to homogenize the yarns to use embedded elements. This is something you may want to look at. Embedded elements in ABAQUS is you have your homogenized ply. Well, your rectangular ply with some thickness, and then you can put inside, you can overlap meshes, and you can put inside the yarns, whatever you have, or maybe simplify somehow these yarns to make them straight lines, or try to see what's the influence. In the end, another recommendation that I want to have is that you can have a very, very complex model from the geometrical side, or you can go for to reduce the complexity in the geometry and to pass this complexity to the material model, for instance. Maybe you are modeling the geometry of your yarns is straight, so that's simple, but you're including the waviness in the material model. So this is something that you can play with. If the geometry is becoming too complex to afford, then try to pass this complexity to the material model and try to see how it goes.
All right, one just last question from Dr. Ali
Yeah.
Mahbub. Yes.
No problem. I have until 12 o'clock. I'm fine.
Hello, Dr. Miguel.
Hello.
I have seen that you have defined an interaction property in your model. So I am interested that for the delamination procedure, what type of interaction property you have defined to relate that with that interply properties. So can you show me the interaction properties?
Okay. Yeah. The interaction that we have is actually the contact between the pin and the part.
Yeah, I
Okay.
want to check that what type of contact conditions you have defined.
Yeah. So this is the property for the interaction, a
frictionless.
conventional, frictionless. You can put here some friction if you want.
Okay.
That is going to change much.
So for the delamination procedure, it will automatically consider the interply properties for the analysis of delamination?
Yes, the interply is only for delamination. Delamination and this contact interaction are separate, are independent. I know. In some cases, if you want to define surfaces, cohesive surfaces, then you have the interaction between the plies, and you have the interaction between with the contact with the pin and the part. Actually, I have that version of the problem as well.
So just a second, can you go to the parts section?
Yeah.
Yeah, so in this part section, this is a single part and you have divided it into two sections, right?
Yes.
So in this, so this is a layer. Okay, the red one. So you have defined this layer as a interaction property between these two layers. Okay.
Yeah, that's
okay.
That is the cohesive surface.
If
you use cohesive surfaces, you have one ply on it, one part for each ply.
Yeah.
And then you assemble them together, and then you define the cohesive interaction.
Okay.
This is when I was saying cohesive elements and cohesive surfaces, that is cohesive surfaces, that interaction.
Okay, I got it. Actually, during meshing, I was unable to see this layer, so that's why I was confused.
Okay. Yeah, here that's why I zoomed in because I thought it would be easy.
Okay, thanks for.
Actually, 1 minute. I have also the cohesive surface version of this problem, so I will make it. I think it should work. So in this case, if we go to parts, we have ply 1. We have only one ply. I can show sections. And if I go to ply 2, it's the same geometry. But well, it changes the orientation. The orientation of the ply changes. And if we go to the assembly, now we don't have any interply in between. I will show sections as well. So we don't have this interply. What we do have is now these interaction properties. And I have to say, this is a bit tricky. If you have to define these cohesive surfaces, it's not so straightforward. Because you have to create your property. For instance, this now it's cohesive behavior with damage. And here we have the interply properties that we had before. These are strengths. These are the fracture energies. We may have some stabilization, well, whatever. But we have damage initiation and evolution. And to apply this, we have to do this, which is is not so straightforward, because you may think, well, I create one interaction for the pin, for the contact with the pin, and I create another interaction for the surface, for the cohesive surface. And like that, at least a few years ago, it didn't work. There was some incompatibility. And what we do, or what we can do, is to create a single general contact like this. This is for explicit, by the way. So, like this, always self. We provide a dummy property. This is an empty property, actually, doesn't have anything. And then we assign the individual properties to pairs. And if we look at this, what we will see is that we have one interaction between the pin and the part. The whole is the part. Well, the two parts in this case, and another interaction, which is the cohesive surface. And like this, it works. Like this, you can define cohesive surfaces in between plies. But this is how it has to be done. I should check for the most recent versions, but at least a couple, 2-3 years ago, you had to do it like this. So yeah, very, very interesting question because it's a practical part that is not so straightforward.
Okay, thank you.
Qasim.
You're welcome.
Yes, Qasim. Qasim, do you have a question?
Yep.
Yes, I have question. Sorry to bother you once again. Can
No
we
problem.
use the same cohesive surface model for the metals, for the
Yes.
simulation of metals rather?
Yes, you can use it for any. It doesn't depend on the material nor anything like that. It's very used on adhesive joints or adhesive
For
joints,
example,
things
I
like.
want to, if if I am working on the rolling process in which different sheets are rolled together and there is some delamination in some part of the sheets, then it can be simulated with the cohesive surface model, right?
Yes. The only thing that you have to take into account is that you have to define these cohesive surfaces in the pre-process. You have to
All right.
pre-insert
Okay.
these cracks, we could say.
All right. Okay. Thank you.
No,
Thank you so
not
much.
like the XFEM or something like that. No, here is like a cohesive plane.
All right. Okay. Thank you.
Just a
You're
small
welcome.
question. Is it possible to model and simulate non-woven plies in ABAQUS or ANSYS specifically for explicit dynamics?
Could you repeat? I didn't hear the last part.
Is it possible to model and simulate non-woven plies in ABAQUS or ANSYS specifically for explicit dynamics?
Yes, yes. ANSYS. I'm not so an expert in ANSYS, but yeah, you can do that. If in the end, if you can do dynamic analysis in any of them, in ANSYS or LSDyna, you can do that. Actually, I know that LSDyna is like the best, most efficient, most robust software for dynamic analysis, especially when you have damage, when you have impacts, these kind of things. But I've never used it. But in ABAQUS, you can achieve also that. You can run explicit analysis. Actually, this last one that we saw with all the damage of the plies, the lamination, is an explicit analysis. So yeah, you can do this. And for 3D woven, for 2D woven, for metals, for any material, you can do that. Take care of the dynamics of the masses that you have, all the inertias that you may have, and start little by little. I always recommend to go little by little. Try to understand all what you get, and start with the most simple model, your 3D woven, completely homogeneous, and see what you get, and then you can start adding more and more details.
All right. Thank you so much. You have invested a lot of time for the community of National Center of Composites Materials, Pakistan, and I would like to thank you for your valuable time. So it was a nice and a long meeting.
You're welcome. I appreciate your invitation. I invite you to take a look at my website. You can find in the blog. You can find many free and useful tips and advice for ABAQUS, for these Python scripts that I was showing. So I invite you to go there. And if you have any question or anything that you want to tell me about, I'll be happy to answer to you. Thank you very much again for the invitation, and I hope to see you again.
All right. Thank you, sir. Bye.
Bye bye.
Bye.